All right, continuing with chapter 7 then, we're still going to be working with this energy stuff. So we've kind of gone over a couple different things. We know a little bit about what work is, we know what kinetic energy is, but now we are going to deal with this new concept of potential energy, right? So we've already dealt with kinetic energy, so let's kind of just summarize everything that we did in our last section, right? So we know when we're talking about work, we're going to need to use all these for this whole thing as well. So we know our definition of work is our force dotted with our displacement, right? So the work being done by some force on some object, take the F dot D, right? You have to have, and again, we can write this as FD cosine of theta. So there has to be some component of the force pointing in the direction of the displacement, or there has to be some component of the displacement pointing in the same direction as the force, right? Whichever way you want to think about it, the math works out to be the exact same, right? So when you have that, right, then your cosine term is non-zero, and you will have work being done by that force. But of course, we also then, if we have forces, we can also say what the network being done by the net forces are. We know that the network has to be equal to the change in kinetic energy of an object, right? So if our object's kinetic energy changes, that means there is some sort of network being done to that object, right? Okay, so then we can say, okay, we also know kinetic energy of some object is given by 1/2 mv squared. This is the energy associated with the motion of some object, right? So if something is already moving, then there is energy associated with that motion, right? Or again, if I do work on some object and I change kinetic energy, it means I either sped it up or slowed it down, right? So yeah, so our force and our displacement, these are our vectors, kinetic energy. Our work, our kinetic energy, this is all scalar, right? So make sure to keep track of that stuff. So let's take a look at then exactly what happens to some of this energy, some of this work that I'm doing when we go back to our simple briefcase example. So if you remember that, we had something like this, right? So we said, okay, here's my little briefcase. If I apply a force up, the displacement is actually up, right? And gravity is pulling down the whole time. This should hopefully be a review still from what we did last time. We know that I did work, right? So we're going to say, okay, the work done by me is going to be F times D. We also know that gravity did some work, right? The work done by gravity is minus mgd. Let's take a look at now this idea of this potential energy. When I pull this briefcase up in the air, right, I'm doing work, I'm exerting energy, but it's not going into the briefcase. Where is this going? Well, if gravity is doing negative work, then in some sense you can kind of think this work is being put into gravity. How does that work? What does that really mean? So in some sense, it still is kind of being put into this briefcase, right? This is what we're going to kind of get at with this idea of potential energy. What we're really doing is we're obviously not doing any net work on this briefcase, right? I've lifted up some sort of height, right? The kinetic energy didn't change. Maybe I did it at a constant rate, or maybe I yanked it up and then stopped it, right? And just kind of held it there or something like that. But the overall point is that I have this briefcase that is now lifted up off the ground. So let's see, where does that energy go, right? Again, we said we can't create or destroy energy. So I am clearly exerting some energy. Gravity somehow is like absorbing the energy. What does that really mean? I'm not sure. Let's take a look at some of the details here and see what we mean with this idea of potential energy. So let's say we take this, right? We have our briefcase and we've now lifted it up, right? I've exerted my force on it and it is now sitting still at some height h above the ground, right? So this is the case that we have here. The briefcase is now sitting still in the air. If I drop this briefcase, what happens? Obviously, it's going to fall down and hit the ground, right? But we can tell right away how much work will gravity do when I drop it. Well, the work done by gravity, if I drop it, will be the force of gravity, m times g, times the distance that it falls, times h, right? And so, in other words, what this is telling us again is this is the work gravity is potentially able to do if I let this briefcase fall a height h. So this is kind of getting us towards our idea of this concept of potential energy, right? I do work on the briefcase, but the briefcase's kinetic energy doesn't change, right? So it's not being put into the motion of the briefcase. What I'm doing when I lift this briefcase up a certain height is I'm putting gravitational potential energy into the briefcase. It's kind of one way you can think of it, right? And if I do this work, right, we can kind of get this energy back by just letting this briefcase fall to the ground. Now, of course, if I do this, right, this briefcase is then in free fall, right? Then we have the work done by gravity is the only force acting on it. as it falls. So therefore, the work done by gravity is also going to be the change in kinetic energy, right? So how does this help us from a problem-solving standpoint? Well, it makes our problem very simple, right? We know we can do our free fall kinematics and all of this kind of stuff. We can figure out, okay, we know what the acceleration is. We can see what the height is. We can figure out the time, so on and so forth. We can figure out how fast it's going at the bottom. We can figure out all these different things. However, we can also look at this problem from the standpoint of conservation of energy. When I let this briefcase fall, gravity is the only force doing the work. This must be, right, this amount of work must be equal to the change in kinetic energy. And so we can write something that looks like this. Say mgh, the potential energy that I start with must be equal to, right, as it falls, what's happening to this potential energy? Well, as this height decreases, right, it gets less and less potential energy, right? It's not as high up off the ground. However, it is speeding up. We are converting that into kinetic energy. And so I started with 0 for my speed here, right? So I started with all potential energy. I ended with all kinetic energy, right? If I let this briefcase fall this height h. So sure enough, we can solve for this v at the end. And what do we get? Exactly what we would expect. The masses cancel out, square root of 2gh, and that's it. It's that simple. And so this is, again, essentially what we're saying is this m times g times h, this is known as the gravitational potential energy, right? So if you have an object that is raised up a height h, it has a mass m, and you're on some sort of planet with gravitational constant g, it will have this gravitational potential energy, right? So again, the kinetic energy is actually associated with motion right now. The potential energy is saying, if I let this object fall, then I can get this amount of work done by this gravitational force, which can then be converted into potential. And then, of course, we know that this is our kinetic energy, right? And so we actually do have a specific term for the total amount of gravitational potential energy and kinetic energy, right? So we're going to call this, it's going to be very important to understand, make sure to keep track of. It's going to be called mechanical energy. And we're going to call it potential energy plus kinetic energy. So these are not the only types of energy that we can have, right? There's all types of different energies associated with all types of different things. So you can have heat energy as well that we'll see. We'll deal with that a little bit. We won't deal with it too much directly, but we'll kind of see when we get into how friction works, right? It looks like friction's stealing the energy, but what it's really doing is it's heating things up. But we have say if the only force acting on it is on some object is gravity, right? Then what you can be sure of is that you're always just going to be converting your gravitational potential energy into your kinetic energy. So this also gives us, lets us look at another concept, right? This idea of conservative forces, right? So here we are conserving our mechanical energy, right? We're saying we start with all potential and no kinetic, and we convert it at the end to all kinetic and no potential energy. So we do need to talk more in general about this idea of conservative forces. And what we're going to say is that gravity is a conservative force. Conservative forces. Gravity is a conservative force, and when you have only conservative forces acting, what you end up with is mechanical energy is conserved. So that's why it's conservative, right? It doesn't have to do anything with politics or anything right now. We're just saying mechanical energy is conserved, right? So it's conservative because it's conserving this mechanical energy, right? Okay, so yeah, so we now have two different types of energy that we're working with. We have our potential energy, we have our kinetic energy. We can see in this system, right, when I'm doing work against gravity, right, I'm doing some work on the briefcase. The briefcase's kinetic energy doesn't change, right? I move it up, it starts at rest. I pull it up, it's sitting there at rest. I have done mgh worth of work on the briefcase. If I then let it fall, I will get all that energy that I put into the briefcase back in the form of this kinetic energy, right? So yeah, so let's look at why, again, looking at things from this perspective of energy is very helpful. Let's imagine we lift our briefcase up again, but instead of putting it on a shelf or something, we put it on top of a ramp. Let's say we have something that looks like this. So I've put this briefcase now at the top of a ramp. This is a nice, smooth, frictionless ramp. And what we're going to say is I don't know what the angle of this ramp is. All I know is, make sure I'm clear, this is not an N. Make sure I'm clear. All I know about this ramp is the vertical height that that the briefcase slides down, right? Now that's the only property I know about the ramp. I don't know how tall or how steep this ramp is, right? Sorry, I do know how tall it is. I don't know how like steep it is. Maybe it takes a long time. It's a very slow process as it slides down the ramp, or maybe it's pretty sharp and it drops off very quickly, right? Either way, it doesn't matter. When we look at this problem from a conservation of energy standpoint, as it turns out, we don't need to know, right? Because look at this. As we said before, this is the main thing why conservative forces and looking at this idea of conservative forces is very useful. If I have only conservative forces acting on my object, I can again be assured that at all points along this trip, the mechanical energy is conserved, right? So in this case, for this briefcase, what are my forces? I have mg going down. I have the normal force pointing up off at this angle. So which force between these two is doing work? Which direction is the displacement? I don't want to draw it as some sort of force, but we know that the direction of that is going to be down the ramp, which is necessarily perpendicular to the normal force. So this is always pretty much going to be the case. The normal force is not capable of actually doing any work. So the only force doing work here is gravity. Gravity is a conservative force, which means I know as this briefcase slides down the ramp, I can conserve my mechanical energy. Well, how much mechanical energy do I start with at the top? Right? I add up all of my kinetic plus potential energy at the top. It's just potential energy, right? It's just mg times h, right? It's just this vertical distance. H is all that matters. And how much, what is all my mechanical energy when I get to the bottom? Right? They have to be equal because I'm just converting from one to the other as I slide down this ramp. It's just 1/2 mv squared. And so we get the exact same result as before, right? So regardless of how long this ramp is, right, how steep this ramp is, if my briefcase falls straight down a height h, or if it slides down some sort of ramp but ends up covering a vertical distance of height h, if gravity is the one doing the work the whole time, the speed at the end will be the exact same, right? It doesn't actually matter how steep this ramp is. And we can actually make this even more generalized than that. Let's say I have, oh no, sorry, I don't want to do this. This is too simple. We already did that one. Let's say I have an even sillier way to slide this briefcase down this height. Let's say I put my briefcase here and I send it on some sort of path, crazy, absurd path like this, right? So this is a little bit convoluted. Obviously, it's probably from a practical standpoint, not going to be able to make it around. But if we can imagine if it does, regardless of which path it takes, when it gets to the bottom, if it's covered this same height h, it can go up, it can go down, right? Like a roller coaster or something like that. It can go up, it can go down as long as gravity is the only force acting on it. By the time it gets to the end here, right? The speed that it will be moving at is still the speed here. It'll just be the square root of 2gh. You can also do it for any point along the trip as long as you know the vertical distance covered. If it's only gone down, say 1/2 h, right? You can do your same thing again. You start with, as you would say, you start with the same amount of potential energy. And if you want to know how fast it's moving here, at this point, the equation that you would write would be this. You have mgh equals 1/2 mv squared plus, see, I go down half an h, plus mg half of h, right? So now what we're saying is I've lost some of my potential energy, but I still have some potential energy at this point and some kinetic as well. And what you'll see is that this extra term here will ensure that I'm not moving quite as fast, but then as you go down at any point along this crazy, convoluted, silly path that I've drawn here, it doesn't matter at all. As long as gravity is the only force acting, then you can be assured that you can figure out what the speed is by just looking at how the kinetic energy has been converted into from the potential energy that you started with, right? At all points along this path, your total energy is this much, and then depending on where you are, some of it will be in kinetic, and some of it will be in the potential. And yes, you can have negative potential energy here. That's just fine as well. Where you define this H from is an arbitrary point. The main thing that matters, it doesn't really matter where you define your H to be 0, because for potential energy, as it turns out, where 0 is defined, it doesn't matter. The thing that's important is how does the potential energy change throughout this problem. So I'll show you some examples where we do some stuff like this, but for now we still need to work through some more Chapter 7 concepts, right? So we have gravity. This is one of our conservative forces. We actually have one other conservative force that we've briefly mentioned but not really dealt with in too much detail. So if we remember, we also have the spring force. This is also a conservative force. If we remember, the magnitude of the spring force is kx, and then the direction of the spring force is in the opposite direction of whether the spring has been stretched or compressed, right? So essentially we're saying if you have your spring and you push it in, right, then the spring pushes out. If you have your spring and you pull it out, then the spring wants to pull back in, right? So the magnitude is this given by the spring constant times x, right? K is in newtons per meter. X is in meters, so the further out you stretch your spring, the harder the spring is pulling on you, is kind of what we're saying here. And this is just this K you can think of as just a measurement of how stiff the spring is, right? The higher K, the stiffer the spring. So let's look at this, right? Let's see what we have. Let's imagine we have some block on a spring, right? And it can slide back and forth like this. Let's say I then take this spring and push it in, take this block, right? And I push it in, it has some sort of mass, m, and I compress this spring a distance x, right? What's going to happen when I let it go? Well, obviously it's going to push back out to the right. But the force that it exerts is not going to be constant. This is kind of why dealing with it from the force perspective or from the acceleration perspective with our kinematics that we've done before is a little bit tricky, right? The force does change, but what I can do is I can talk about the average force, right? When I push it in at this point here, the magnitude of the force equals kx, right? And then as it keeps pushing it out, but the force gets weaker and weaker and weaker, right? As this spring keeps pushing the block out. When it gets back to its resting position, what is the force? The force is actually 0, right? There is no longer, now the string is at its resting length, right? It is neither stretched nor compressed, and so the spring will not be applying any force. And all along these points, as this spring pushes this block back out, what you'll see is that the force gets weaker in a linear fashion from a strength of kx all the way down to a strength of 0. So what is then the average force over this distance? It's 1/2 kx. So now with this, we have what the average force is, right? We started out with a strength of kx. It decompresses, and it goes all the way back to its resting position, and now the force is 0. The block is moving, right? So don't be confused about that. We have accelerated the block is moving, but the force on the block at this point, once it gets back to its original length, is 0. How far did it go during that time when it went a distance of x? And so with that, we can actually figure out what the work done by this spring is, right? So the work by the spring in this case will simply be the average force times the displacement, which in this case is x. And so the work done by the spring over this distance as it decompresses will be 1/2 kx squared, right? And so this is the work done by the spring. This is actually also the potential energy that had been stored in the spring, right? If I take this spring and I squeeze it down and I compress it, right? It's very analogous to, when you lift a book up onto a high shelf, right? If you stop holding that book there with either with your hand or the shelf or whatever it happens to be, if the book is allowed to fall back to the floor, right, the book and the earth, because of their gravitational pull, will accelerate back towards each other. Whereas in this case, again, if you stretch this spring out or compress it, whichever way, right, when you do that, you're putting potential energy in the spring, and then the spring will want to either snap back into position or compress back out extend back out the other way, right? So gravity only works in one direction, but the spring force can be in either direction depending upon if you stretch it or compress it. And so again, what we're saying is the potential spring energy is this right here. It's 1/2 kx squared. So if I take this spring and I compress it in at distance x, I have stored 1/2 kx squared worth of potential energy within that spring, right? So let's say we do this, right? And I want to know, I push this block in a distance x, however many meters that happens to be, probably a few centimeters or so. And then I want to know how fast is this block going when it gets back to the resting position, right? I push it in, I let it go, the block comes back out. We can again look at our conservation of energy method for solving this problem. We can say we started with when it was compressed, right? When it's compressed, we have 1/2 k x squared worth of potential energy. At the end, the block is now moving. The spring is decompressed. There's no potential energy left in the spring. And so all of that energy is now 1/2 mv squared in the kinetic energy of the block, right? So then, of course, you can say how fast is this moving? You can simply solve for v, right? So in this case, with the 1/2 will cancel, but there's no m to cancel, right? So it does actually depend upon the mass of the block this time. And so we can say v is equal to the square root of 1/2 cancel. We get kx squared divided by m, right? And so a stiffer spring and pushing this spring in further will cause it to move faster, but of course a larger mass will cause the block to be moving more slowly, right? So again, our spring force is also a conservative force, and so what we're seeing is this is going to be true every time, right? These are only going to be the two conservative forces that we work with. There are others, but what we're going to see is that conservative forces give rise to potential energy, right? So if we have a conservative force, then that guarantees that there will be some type of potential energy associated with that conservative force. Again, when I take a book or a briefcase and I move it off the ground, right, or in this case, I guess I should do it like this, and I let it go, gravity will ensure that it falls back down, right? So there's potential energy, right? How much energy could gravity potentially do if I let it fall back to the earth? With the case of a spring, again, if I stretch it, the spring will potentially be able to do work to, go back to its resting position, right? Or if I compress it, the spring will extend again and do some work potentially in that manner, right? If I let those conditions happen, the spring force or the gravitational force will attempt to will convert that potential energy back into kinetic energy given the opportunity, right? So again, as we said before, if only conservative forces are acting, we're going to kind of do a little bit more formalized proof of this. So we can say if we only have conservative forces acting, then our mechanical energy is conserved. So how can we show that? How can we prove that? Well, we can think of it this way. The work done by a conservative force, right, has to be equal to this, minus the change in potential energy, right? Whenever gravity is doing work or whenever the spring force is doing work, right, that means that there is already some gravitational potential energy or some spring potential energy that it's pulling from, right? That's the only way gravity is able to do work. There has to be some sort of potential energy there for gravity to draw from in the first place, right? So again, you have something raised up a certain height, you let it fall, gravity does positive work on that object, which means that object then loses potential energy. So the work done by conservative forces is always equal to the negative change in potential energy of your system, right? However, if only conservative forces are acting, forces act, then what can we write? Then we know that the work done by conservative forces is also equal to the net work being done, right? If there are no non-conservative forces, then this is also by definition going to be the net work being done. And the net work being done, as we know, is the change in kinetic energy. So that, of course, lets us write this. We now have our delta KE is equal to minus PE, or the change in potential energy plus the change in kinetic energy has to equal 0, right? Our potential energy can change, our kinetic energy can change, but when we have only conservative forces acting, right, how they change, they can only be converted from one to another, right? You can convert kinetic energy back to potential energy, you convert potential energy back to kinetic energy, but you can't ever change the total amount of these two together. So the general formula that you have for your problem solving when you have only conservative forces acting, and we will see examples where we have non-conservative forces, but we're not quite there yet. But when we have only conservative forces acting, you can look at your system. You can say the kinetic energy initial plus the potential energy initial has to be equal to the kinetic energy final plus the potential energy final, right? So yeah, so if you look at your system again, as we had before, just these simple examples of, say, a book falling from rest, right? The initial kinetic energy was 0. The initial potential energy was some sort of gravitational potential energy. The final kinetic energy was then whatever it had at the bottom, right, when it fell that distance. And then there was, of course, no potential energy afterwards. But again, this will work for at any point along that book's trip. And so, of course, maybe you can toss the book down and then it would have some sort of initial kinetic energy. Maybe you can see what it maybe you want to know what the kinetic energy is after it's only fallen half the height, and so there would still maybe still be some potential energy afterwards. You can also do it the other way around, right? You can say you can throw a book up in the air. You can say, okay, give it some kinetic energy. How high is it going to go, right? And you can see what that change in potential energy will be as well. So again, to summarize, this is our formula that we can use if we have only conservative forces acting, right? Figure out what your kinetic energy is at the beginning, figure out what potential energy is at the beginning, and set it equal to your kinetic plus potential at the end. So we know our kinetic energy is equal to 1/2 mv squared, and we have the potential energy due to gravity, which is mgh, and we also have the potential energy due to the spring force, which we'll sometimes come across, which is 1/2 kx squared.